Okay, so we're going to go ahead and start with the next session. So this session is about the Simons-NSBP Scholars Program. And my name is Casey Wagoner, and I'm going to be just discussing the program a little bit. And I'm speaking on behalf of myself and Saran Lee Johnson, who is over in the corner. Saran and I organize the program. And so I want to start by just giving you a little bit of an introduction to what the program is. First and foremost, this is a 10-week research program for undergraduate members of the NSBP. The projects are conducted by students living at and working at the Flatiron Institute. The Flatiron Institute, if you don't know it, is a really awesome research space. It's in New York City. So as part of the program, you as a student would live in New York City, all expenses paid for your travel, your housing, everything about it. In addition to the research experience that comes with the program, there are a number of other things that we built into it that are specifically targeted to give you all the best experience possible. A little bit more about the program. It's a partnership between NSBP, the Simons Observatory, which is a collaboration of scientists that study cosmology. They're measuring the cosmic microwave background, and the scientists at the Flatiron Institute. We do research projects with people in all of these areas, so astrophysics, quantum physics, cosmology, biology, neuroscience. So it's really a broad array of potential projects that we have for anybody that's interested. I mentioned we have some other things. Every week as part of this program, there's a research talk from a different Black physicist. There's, as we're seeing at this conference, if we didn't know already, there are a ton of Black physicists that are doing awesome work. And so these are research talks that are introducing you to the various different areas of research that are being done all around the country, and some of them are even around the world. We also have a series of workshops where people will talk about and give their career advice. This particular set of pictures is from a workshop that we did in 2021, where we had somebody who is a professor now in neuroscience and somebody who is a PhD physicist, but he's working at Intel, working on, trying to build the next quantum computer. We also every year visit the students that are a part of the Harlem Gallery of Sciences mentoring program. And so the idea is that our scholars can go and reach out and connect with a younger set of students, show them all the awesome things that our scholars are doing. All right, and be role models for that younger generation. And so this is a picture of some of the people that we visited during this event this past year. We also every year visit a graduate school. And so this is this past year, the picture on the left, we visited the University of Pennsylvania. The physics department there set up a sort of a private guided tour. We got to see labs. We got to talk to people, current graduate students and faculty, about what it's like to be in their graduate program. We also got to just kind of walk around Philly a little bit. The year before, in 2020, pictured on the right, we visited Princeton University. And this is actually a picture with most of our scholars that made the visit circled around Einstein's desk. All right. And so that was kind of a cool, unique experience that we got with the visit to Princeton. We also always have some kind of somewhat random additional activities. So this past year, at the beginning of the program, we visited this sort of art science installation that was at this space in New York. It was called The Life of a Neuron. And what it was this cool music visualization of what it was like to be in the human brain from the inside as it ages. So from the moment of birth all the way through the moment of death, and showing what happens with the neural circuits inside of a typical human brain. In 2021, we actually did a virtual tour of the CMS experiment at CERN. So we had somebody on a GoPro, went down into the experiment hall and was showing us exactly the different parts of the experiment there at CERN. This past year, we did something new where we had a poster session at the end of the summer. And so our scholars, what you're seeing here, actually, this is the back of Kana, and this is Jay Wheeler presenting a poster about all the awesome work that they had done throughout the summer, and various students or various scientists at the Flatiron Institute came and learned about all of this work. So that's a bit about the program. What we're going to do now is kind of move on and highlight some of the scholars that have been a part of the program. This is just a very small sample of the many scholars that have been a part of our program in the past. And so what we're going to do is we're now going to hear a series of 3 different talks from scholars on the projects that they did while they were part of the program. And then after that, we're going to have a panel discussion with 4 other alumni of the program to just talk about what the program was like for them, and maybe give advice for anybody that's thinking about doing the program, thinking about applying, and just, to get a feeling for what it's like from the scholar's perspective. And then finally, I'll wrap up with just a quick note about how you can be involved. That is, if you're a student that's in the audience, what you need to do to apply, or if you're somebody that's beyond undergraduate years, but what else you can do to be part of the program. So with that in mind, I want to invite onto the stage our first speaker, which is Kana Smith. So Kana, if you want to come out.
Can anybody hear me? Yeah, okay, perfect. Hello, everyone. My name is Kana Smith. I am a 5th-year undergraduate student at the University of Toronto. And this summer, I was a Simons-NSBP Scholar, interning at the Flatiron Institute at the Center for Computational Astrophysics. And so I was working on a project with Lisa Bounier and Arthur Lasso titled Unveiling Stellar Nature Through Oscillation Pattern Recognition. And this was a project on astroseismology. So we've been researching red giant stars for this project, and these are stars that have evolved off of the main sequence. And so for reference, the sun is currently a main sequence star. So during this evolution, the star's convective envelope or outer layer is expanding while the radiative core is contracting as it continues into its next evolutionary phase. And so for this project, we were looking to classify 4 different types of red giant stars. Those include red giant branch stars, red clump, secondary red clump stars, and lastly, low amplitude or depressed stars. And so these depressed stars, of which are found on the red giant branch, are stars that developed convective cores while on the main sequence. And so it's hypothesized that a magnetic field is induced within these depressed stars due to the driving of plasma in a dynamo effect. So we're looking to classify these stars based on their oscillation patterns. But what exactly is an oscillation pattern? I just spoke about the stars having radiative interiors, and this creates turbulent environments, inducing both acoustic and gravity waves in the star. These waves are shown traveling through the star in the first figure. And so acoustic waves, illustrated on the left of the second plot, give us characteristics of the near surface, while gravity waves, illustrated on the right of the second plot, give us characteristics of the deep stellar interior. Acoustic and gravity waves increasingly couple, known as mixed modes, during stellar evolution, and this happens inside the cavity between the radiative envelope and the convective core. So this is again because the core is contracting and the envelope is expanding, and the result is that the acoustic and gravity waves begin to couple because they're becoming closer in frequency. And so the focus of this project will revolve around the dipolar mixed oscillation mode L=1 that travels directly through the stellar core and is seen on both plots. Additionally, the parameter L simply denotes the number of surface nodes that the wave has. Like the title states, the objective of this project is to classify red giant stars based on their oscillation modes. Stars will present different degrees of coupling in the L=1 oscillation mode based on their evolution, which is why L=1 has our focus. On this figure, we can also see that region between the core and the envelope where the mixed modes are coupling. And so this image originates from one of the papers making this hypothesis about the interior magnetic fields in depressed stars. To get started on our work, we obtain our data from the Kepler Space Telescope, which hunted exoplanets using the transit method. We can see an example of this in the figure on the right. And so by monitoring stellar light curves for significant brightness changes, we're able to locate planetary systems. Because of this mission, we now have light curve data from the red giant stars to analyze. And now you may be wondering how these light curves fit into our project. So the oscillation modes I mentioned earlier cause the amount of light emitted by the star to flicker in time, but within specific frequency ranges. So when we take those light curves and translate them into the frequency domain using a Fourier-like transformation, we get what's known as a power spectrum density diagram, which can be seen on the left. Highlighted here, we have the region where the star is oscillating, although it isn't obvious to point out. So we instead look at the same plot, but with a logarithmic scale, like on the figure on the right. We can now see a more well-defined bump in the data highlighting this active region. And when we magnify this same region, we see the oscillation modes L equals 0, L equals 1, and L equals 2. And again, these numbers tell us the amount of surface nodes that the wave has as it travels through the star. Now with this magnified power spectrum density, we create what is known as an Echelle diagram. And we do so by vertically slicing the diagram into sections of delta nu, which is just the distance between consecutive L equals 1 modes. We then take these slices and we stack one on top of another like the rungs on a ladder, hence the name Echelle, which is French for ladder. And so the bright spots on our Echelle diagrams here represent the higher points of amplitude from the power spectrum density. The example star here is a red clump star, and we can tell by looking at the L equals 1 oscillation mode, which is furthest to the right, which shows fine scattering. And in contrast, we also have the Echelle diagrams for the other stars we're classifying. And from left to right, we have the red giant branch, which shows slight scattering, but is mostly linear. Again, we have the red clump star. Then there's the secondary red clump star with more prominent scattering. And lastly, at the end, there's the low amplitude or depressed star with no visible L equals 1 mode. Again, it's hypothesized that an interior magnetic field traps the L equals 1 oscillation mode in some red giant branch stars that we classify as depressed. And the scattering in the L equals 1 mode here, again, is representative of the amount of acoustic gravity wave coupling, which increases with evolution. Now that we have the Echelle diagrams generated for each star, we can begin classifications. First, we feed the Echelle diagrams to a convolutional neural network deep learning algorithm developed by Google for image and object detection. The typical output of this algorithm is a classification based on the algorithm's image library. But since it's unfamiliar with our Echelle diagrams, we instead take the penultimate layer from the neural network. And this gives us a long 1D vector weighing the image characteristics. We then take this 1D vector and we reduce it using TSNE, which is an algorithm for multidimensional data analysis. And the output of this is a 3-component vector, which we finally feed into a spectral clustering algorithm titled nearest neighbors, which groups the 3-component vector for each Echelle diagram based on their proximity or similarity to one another. With this classification complete, we now have our results. And so the images here are a 2D projection of the 3D map that was created using the previous 3-component vectors. And so each color here represents a group of red giant stars that have unique oscillation patterns. When we initially receive the data, the clusters are undefined, but the plots are interactive. And so hovering over each cluster shows us the type of stars they are, and we're able to label the diagram. And here is the main classification of my project, where we can see clusters for the red giant branch, the red clump, the secondary red clump, our depressed stars, as well as a few unclassified clusters. Similar classifications to ours have been done previously. With Han, Stellar, and Yu from 2017, they used the magnified power spectrum density diagrams seen here and fed them into their neural network. Their network was trained to classify stars strictly as either red giant branch or red clump stars, whereas our approach differs from theirs as we fed the Echelle diagrams to our neural network, and our network was trained more broadly to classify images. With this flexibility, we're able to separate unusual stars, which we marked as unclassified for later evaluations. In contrast, the previous work would have classified the points as either red giant branch or red clump stars, which is a more rigid approach. Additionally, our usage of Echelle diagrams may have classified the stars better, as characteristics of their oscillation patterns are more prominent in our Echelle diagrams than they are in the power spectrum densities. With their data, we can also see some gray points at the very bottom in the top right figure that represents newer data, which at the time did not have the necessary pre-data calculated to do this type of classification. But during our work, we did have these values and were able to automatically classify around 18,000 Kepler red giant stars. And here is a more direct side-by-side comparison between the two plots of our final classification. And so these diagrams illustrate stellar evolution from an astroseismic perspective. So to conclude, did I successfully complete my project goal? And the answer is yes. I was able to classify around 18,000 Kepler red giant stars based on their oscillation patterns. And some next steps for this project would be to remove unusable data from the stars that were either observed for an insufficient amount of time or have incorrect predata. Investigate the unclassified stars to identify whether the data was unusable or if there's another star type that we haven't considered yet. We may also experiment with more clustering algorithms to see if our results could be better. And most importantly, we would continue investigating into what is causing the suppression of the L=1 oscillation mode in our depressed stars. Thank you for your attention, and I'll be available for questions at the end.
So thanks, Kana. So I forgot to mention that in the interest of time, we're going to wait until all three of the speakers go. And then if there is a question, we can address it at that point. So with that in mind, I'm going to ask that the next speaker, Oge, come on to stage.
Hi, my name is Oge Okoronkwo, and I'm a recent undergraduate grad from the University of Oklahoma. And over the summer, I spent my time at the Flatiron Institute understanding isolated LMC mass analogs and their satellites. And I had the pleasure of working with Dr. Allison Brooks, representative of Rutgers University. So the main goal of my project is to identify isolated LMC mass analogs, and I analyze their interactions over time using two different smooth particle hydrodynamical simulations, Romulus 25, and then another high resolution zoom-in simulation. So you're probably asking, what is the LMC for those of you who are unfamiliar with astro terminology, but the LMC is short for the Large Magellanic Cloud. And it is a dwarf galaxy about 10 times less massive than our home galaxy, the Milky Way. And a satellite galaxy is a smaller companion galaxy which orbits a more massive and luminous host. And the LMC is the largest satellite galaxy of the Milky Way. However, an isolated galaxy is not bound by the gravitational potential of another galaxy. And in this project, we want to understand the distribution of satellites around an isolated LMC mass galaxy. So why do we care about LMC galaxies? Well, it's because recently astronomers and astrophysicists have been trying to answer the question of just how many satellites of the Milky Way are actually from the LMC. About 1 billion years ago, the LMC was once isolated on its own, and it had its own satellites orbiting it. And photographic surveys and recent digital surveys have helped us to map out the Milky Way and its environment around it. So here in this image from Gaia, horizontally spanned across is the Milky Way galaxy. And then here we have the LMC and its satellite. The only remaining satellite of the LMC is the Small Magellanic Cloud. But recently, scientists have just been trying to answer how many of the Milky Way galaxies actually belong to the LMC. And from the Dark Energy Survey, there is this area right here in purple of unidentified ultra-faint dwarf galaxies located within there. And just because of how close in proximity it is with the LMC, it brings up the question of how many of those once belonged to the LMC at one point. So the first simulation that we use to make our models is the Romulus 25 simulation. So this is a large cosmological simulation, about 25 megaparsecs per side in the box. And it contains thousands of different galaxies and large scale structures. So you have Milky Way sized galaxies, Andromeda sized galaxies, dwarf galaxies, groups, clusters, and so on and so forth. And this was great because it allowed us to look at a variety of different environments. And here in this blue box here is the whole cosmological simulation, and we were able to pull out an LMC size galaxy from the simulation pictured here. And right off here, off center, is one of its satellites. So these are the galaxies that I'm going to be working with in this project, or that I worked with in the project. So in the Romulus 25 sample, we were able to detect over 300 LMC-sized isolated galaxies, and imaged here on the left-hand side in the big white circle is an LMC mass galaxy, and around it, it has 5 different satellites within the red circles. And there were about 59 satellites detected out of the 300 analogs that we had. And so here on the left-hand side, I have a satellite mass distribution out of all 59 satellites. And if you notice, there's something a bit strange about this histogram here. It identifies 10 satellites with mass 0. So this is where we ran into an issue, because we know that's not the case. However, Romulus wasn't able to identify any ultra-faint dwarf galaxies, which is why we use another simulation. Here we have the high resolution simulation. So we were able to use another database and cross-reference and pull out 3 different halos from Romulus and get a zoom in face-on image of the 3 halos. So we have Halo 488, 597, 431. And this simulation was great because it allowed us to look at internal structures of smaller dwarf galaxies. And we wanted to use this in the future to be able to resolve internal dynamics such as quenching and disruption, and if there is any host to satellite interaction. And so I plotted a scatter plot to compare the 2 different simulations, just to see just about how small of a scale and how much smaller masses that the high res simulation could pick up. And so here I have a scatter plot. And so these are the 3 high resolution zoom simulation analogs compared to their Romulus counterparts. And you can see that they do have a higher virial and stellar mass. So they were able to pick up a lot of the smaller stellar populations that Romulus could not. And so that was really helpful to know that we were on the right track to something. And just to show for it, I plotted satellite luminosity functions for both of the simulations. So here I have all 59 of the Romulus satellites. And so the smallest that it could detect was down to 10 to the 7th. But for the higher resolution simulation, it could detect down to about 10 to the 4th. In Romulus, it could not identify any satellites from Halo 431 though. So this is a great thing to note. So I started to begin looking at disruption and interaction between host satellites. So with using Halo imaging in Romulus, I noticed that there was a satellite which looked to be a bit disturbed. There was elongation around like the outer rim of the galaxy. And so we took a definition of tidal index, which measures any disruption going on within the halo, and measured the tidal index. So the higher the tidal index means the more disruption that there's going on within the halo. And so for Halo 1724, the tidal index continues to grow throughout the course of the age of the universe. And so I knew that because of the tidal index disruption, there had to be some sort of either like missing gas or like what is going on with the stellar population. And I wanted to know how that affected star formation history. So I made a star formation history plot here. And this plot here is interesting because it shows how active the halos are within star formation. So this is star formation history for all of the LMC satellites in Romulus. And the larger satellites are depicted here in pink, whereas the smaller ones are depicted here in blue. You notice that the bluer ones are more active in star formation throughout the course of time, whereas the purple ones, they are very active in star formation and then they level off here. And that's something opposite of what we would normally expect. So for future work, I plan to use the higher resolution simulations to determine what the dominant form of quenching mechanism is going on within the halos, and to study the quench fractions as a function of definition and mass. So I'd like to say special thanks to the Simons Foundation for having me over the summer, And also shout out to my mentor, Allison, and for my research collaborators from the University of Oklahoma, and also to Casey and Saron and Shannon. And then I'm also open to any questions after this is done. So you can just find me out in the lobby or anywhere in the Omni. Thanks.
All right, thanks, Oge. So our next presentation is going to come from Latoya Anderson. So Latoya, if you want to come out.
All right, so good afternoon, everyone. Oh, sure, thank you. Okay, awesome. So good afternoon, everyone. As Casey said, my name is Latoya Anderson. Thank you so much for coming today to learn more about the Simons Foundation and the Scholars Program. As you can see here, I am an undergraduate physics student at Brooklyn College, and I am now an associate research analyst at the Simons Foundation, also known as the Flatiron Institute. So we have this beautiful photo of our 2021 scholars that I was a part of. That's where I actually got my start at the Simons Foundation. And my research project that summer focused on learning how to calculate the electronic structure of materials. And so that involved learning how to use Quantum Espresso, which is a software program that's designed to run quantum chemistry and solid state and condensed matter calculations. And I did this on the high performance computing cluster. And just to kind of give context, never done any of this before. So I'm learning literally right there at the foundation. I also learned how to use this Python program called the Atomic Simulations Environment. And so the short version is ASE, so which is what I'll refer to it just for this slide here. And what's really awesome about ASE is that because it's a Python program, most folks are most familiar with Python. You're again able to run condensed matter calculations or electronic structure calculations. You can also use it to drive other programs to run your calculations. And that was what I did by driving Quantum Espresso. Then from there, I learned how to use yet another Python package called the Python-based Simulations Chemistry Framework, short for PySCF, and does the same thing, but with the addition that it also has molecular dynamics calculations that you can run. So my project focused on not only learning all of this software, but how to connect PySCF to ASE in order to drive electronic structure calculations. So that set the groundwork to then do what I'm actually doing now. I am studying something called superatomic crystals. But to kind of take a step back, superatomic crystals, they are made of superatoms. And so a superatom is this cluster that you see here. And what's really unique about these clusters is that they mimic the properties of traditional atoms, but they vary in size between a molecule all the way up to what's called a bulk solid or a crystal, essentially. So structurally, they are very complex, which is really important because that allows us to tune for its magnetic, photonic, and electrochemical properties. Now that we have a sense of what a superatom is, put them together, now we have a superatomic crystal. And so that's what we're actually seeing in this photograph. What's really amazing about these crystals is that by having them be assembled together, they tend to have highly delocalized electronic structure. What does that mean? We can essentially play with its valence electrons to get the properties that we're looking for. Now that we have that sense, it shows us that we have exciting opportunities to be able to build new and exciting materials so that we can improve things like solar panels, quantum computing hardware, etc. So my system that you've been looking at this entire time is this system here. It's a 16 atom system and then expanded out to a 2-dimensional material, and it's composed of 6 rheniums, 8 seleniums, and 2 chlorides. When we have our stacks, which is what we're looking at right here, so we have this one stack here, one stack here, you'll notice is that they're not necessarily bonded together, but they do have weak interactions. These are van der Waals interactions. And so that allows the mechanical or the materials engineers to be able to mechanically exfoliate down to its two-dimensional structure. So this here is a side view. So if we were to look at this one layer here from the top down, that's what we're looking at right here. So these crystals or atoms, superatoms, are bonded covalently. They have a very strong structure, right? So like I said, that allows for that mechanical exfoliation. So why are we studying this? We are studying this because at room temperature, it has semiconducting properties. So that's of interest. But at the same time, because this is a new class of materials, we need further study into what these can do. So how do we study this? We use something called density functional theory. And essentially, the long story short is that instead of looking at all of the different energy levels that these electrons can occupy, we actually look at its electron density. This reduces the computational complexity. It basically is a great way of being able to understand what's happening with our system, but at the same time, reducing the computational expense. We can then understand its crystal vibrations, and like I said, the electronic structure for atoms, molecules, and solids. So this is where we bring in band structures. So when we run these calculations, and to be clear, DFT for short, density functional theory, it's something that's programmed already within Quantum Espresso. And so once you run this program, you plot its band structures, and band structures essentially are telling us where all of the occupied energy levels that these electrons can either be in or already most likely are. So down here, we have our valence bands, right? So just like in your chemistry class with the valence electrons expanded out to a crystal solid, we now have our band structures. And what you'll notice that these are relatively flat. That's awesome. We like that. The next thing is that we also have our conduction bands up here. And those conduction bands are basically the likely locations that the electrons can actually jump to when this material has been excited. So the next thing we look at is our band gap. How much distance is there between the valence bands and the conduction bands? And so far it's been measured to be between 1.1 to 1.5, depending on how you run your calculation. The disadvantage with DFT is it's not great about predicting band gaps. It gives you a pretty good idea of what's happening. That way you have to do extra steps to understand your material. Now, the next step is doing its projected density of states. The long story short, that's really most important is that thinking back to those band structures that we saw before, this side here are the valence bands. And you'll notice this. So this here is the rheniums, this here is the seleniums. We're talking about the orbital contributions to the energy of this system compared to the chlorine or the chloride. You notice that it's much larger, and that's what we're looking for. This gives us a better understanding of our material. This side here, and here, and here, that's the valence band side. And the one that's giving the most orbital contribution would be this right here. So again, that's important. So in summary, what I did was I studied the electronic structure of my superatom, which is composed of those 16 atoms, plotted its band structures, and then run its projected density of states, so all those atomic orbitals that I mentioned before. We saw that there were weak interactions between those atomic orbitals, which is great. That's what we want. And then on top of that, we actually measured the band gap to be about 1.1 electron volts. Finally, what is the next step? The next step for me is to now develop a Python module, which will hopefully be able to be pushed to PySCF. And that Python module is going to use the tight binding method, which is another type of approximation that will calculate those band structures with hopefully a greater degree of accuracy, or at least gives us a little bit more information than what DFT can give us. So if you want to learn more about my projects that I've done at the Simons Foundation, always plug. Feel free to scan my barcode and you can see, or my QR code, and you can visit my website. Feel free to see all my projects. Go to the Simons Foundation. You'll see all the cool stuff that's there. I'm with CCQ. And with that, thank you.
All right. There we go. Is that what you want? All right. So maybe we could have all of our speakers come on stage and give them one last thank you. And there's opportunity for time for a question if anybody has it for any of the speakers. I guess what I would ask, I don't think we have a mic runner, but if you have a question, you could come. Oh, we do have mic runners. Great. So maybe raise your hand and ask a question. All right, ladies, come on. Anybody? That's all I have. So they're just going to a question.
Oh, okay.
Thank you. Okay, so my question goes, the first speaker. Yes. Very nice presentation, by the way.
So, thank you.
Yeah, so I would like to know, like, out of curiosity, do you have any idea of how, it's like, the density of those stars, how they vary with their depth?
How the densities vary?
Yes, with respect to the depth of those stars, like from their center to the exterior surface.
So thank you for your question, first of all. As the stars evolve, I know that the cores are becoming increasingly dense. So that's why the core is contracting. And so that increase in density, we don't directly study it, but I'm aware that it does impact the amount of coupling that we see, the acoustic and gravity wave coupling. And so that's why we see more prominent scattering in the L=1 oscillation mode. But we don't really focus on the density as much because what we're focused on is the fact that when the core contracts and then when the envelope expands, we have a larger cavity between the two. So that gives more room for more coupling, but the density does increase as the stars evolve. Thank you.
Use the deep learning procedure to like analyze your images. So do you mind throwing more light on your cross-validation technique? Like, how were you able to assess the efficiency of the models you used?
I might ask. I might interrupt and ask. Maybe you guys could talk
Yeah, for sure.
individually about that. I think it might be more efficient, both time-wise and discussion-wise.
Yeah.
Is that cool?
Yeah, thank you.
So could we give a round of applause for the speakers again? All right. And really, I would encourage you, they're all fantastic. So I would encourage you, if you have more questions, to find them and, chat with them. All right. Thanks. Thanks, ladies. All right. So at this stage, we're actually going to move on to the next part of this program. And what we're going to have 4 different alumni of the Simons-NSBP Scholars come out. And we're just going to talk about their experiences in the summer program, just to give a flavor of what it's like for anybody that's in the audience that might be interested. You guys want to come out? So my hope is that this part of the session is somewhat informal in the sense that, I want them really to just talk candidly about what it's like to do this. I don't know how everybody feels, but sometimes like living in New York is overwhelming, going to a new place, working on a high level research project. So I'm hoping that just they can give their perspective on that. But before we start, I'm just going to ask each one of you to kind of go. We'll start with Jade. Just introduce yourself, tell the audience where you're a student, and just tell like a 1-sentence summary of the project you worked on in the program. So Jade, and then we'll move down.
Okay, so can you guys hear me? Okay, perfect. Hello, everyone. My name is Jade Moore. I am a 4th-year physics major at Jackson State University. I was a part of the NSBP Scholars Program in 2021, and I worked with the Simons Observatory. So I did astrophysics.
Hello, everyone. My name is Jay Wheeler. I'm a 3rd-year physics major at Davidson College. I worked at the Center for Computational Biology, looking at tooth development, specifically the creation of enamel.
Hi, everyone. My name is Lawrence Edmond. I am a first-year PhD student in theoretical physics at Brown. In 2021, I worked at Flatiron in the Department of Computational Astrophysics on a project working with gravitational waves.
Hello, everybody. My name is Nathaniel Kahasai. I'm a third year at UNC Chapel Hill, and this summer I was working with Simons Observatory, working with mirror alignments for that project.
All right, so now I have a set of prearranged questions I'm going to ask, but if anybody is in the audience, I really, this is a great opportunity to get to, ask a question. So if you have a question that you would like to ask the panelists, feel free to raise your hand and, we'll bring the mic around. But maybe to start, I'm just going to ask, was there anything that you all felt like was a particularly interesting or unique opportunity that you had in the Simons-NSBP Scholars Program? And maybe just speak to what you liked about it, something basic or something intricate, whatever it is. Lawrence, I'm going to ask you to start. You're a charismatic guy.
Yeah, okay. So I think probably one of the most impactful things that happened at the NSBP was being exposed to so many physicists who also looked like me, working on some very intense projects at the time, at the time of when I first went to Flatiron. So I guess to give a little bit of context real quick, I was in my junior year. I was finishing up my junior year of undergrad when I had the opportunity to go to the Simons Foundation and work on my gravitational wave project. And that was the first time I really had exposure to computational astrophysics of that degree. We had access to like cutting edge simulation or cutting edge numerical relativity simulations that allowed us to see the like curvature of space-time around merging black holes in detail that I didn't even know was possible with current technology. And on top of that, I had the opportunity to work on these projects around peers who looked like me. And at that time, that was 100% game-changing.
Yeah. Anybody else want to contribute, or we can move on to another question?
I can contribute. I think that something that was unique to this experience was just the sheer amount of resources that they had access to. The Flatiron Institute is amazing. Any possible question that I could have had, any problem that popped up in my code or something that I didn't understand, oh, just go to such and such's office on the second floor. They're an expert in that. And you could literally knock on their door and they'll say, hey, and you can sit there and talk to them about any problem that you could have. And these are people with PhDs who are willing to sit and talk to any problem. They're looking at your code, your horrible, horrible Python code, trying to figure out, what you are going for. And they will sit there and help you out of their personal time and give you anything that you need. And it's because they understand how valuable this experience is. And I think that they want to make it as impactful as possible. And that was something that I feel like is very hard to find at other institutions and other programs. Somebody who's willing to take out that time and invest in you. People who don't even know you, people who don't personally have interns, they take you in as their own for any issue that you might have. And I think that's very unique.
So I actually have a hard time seeing. I don't think there's a question from the audience yet, which is totally fine. I'll move on to more of my own. What about, let's see, was there anything that was particularly memorable for you all? And I think I'll start with Natu and Jay. So either one of you want to go?
Yeah, I can go ahead and start on that by saying that I would definitely say like the most memorable part was like seeing like an actual like lab for the first time. Like part of the work was done at UPenn, where we later did a tour at, so all scholars were able to see that. But for me, for a long time, having always done stuff in my garage and getting whatever was like the cheapest thing on Amazon that I could work with, or such and such, or like just using my dad's toolbox to see like, whoa, this is like a place where like actual research happens. This is like they have state of the art, top of the line. It really felt like 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 a playground, like, you know, a kid in a candy store type feeling. That was really memorable for me, and that kind of like affirmed to me like, yeah, this is like kind of what I want to do, especially if like I recognize I'm kind of having this like reaction right now being here. And on top of that, you know, pairing that with, you know, a community for the first time, working with people that looked like me, and also, you know, able to talk physics and not, you know, have to have all the negative connotations of, you know, being the only one that looks like me trying to talk about physics in a room. That was really uplifting.
Yeah, so for me, the most memorable experience was probably at the end of the program where we gave presentations, a talk. I was very scared. I'm not a big public speaker. I was like, what if I say something wrong about my research? But it was an amazing experience, not only to hear what my peers were doing, but also actually, because people keep asking like, okay, what do you do? What about teeth? Why is that important? To actually explain that and explain it with confidence was amazing. And also, we had Dr. Jim Gates invited to our talk, and he asked me a question, and I was like, wow, this like well-known physicist is asking me a question. And I don't know, that was just so cool to me, because I'm like, I don't know the answer to it, but thank you for asking. But yeah, like just it was like a really good end to the program. Like, okay, I did do something, I did take away something, and I did it well, and people loved it and liked to hear about it. So yeah.
I'm curious if any of you, if there was anything that surprised you about the summer that you spent in New York, whether it was, you know, the actual research or, you know, just being there, or, you know.
I can say that I was surprised how quickly I was able to connect with my group.
Okay.
I think I was going in nervous. Especially, I am from Mississippi, for you that don't know where Jackson State is. And I would say this might be a reach, but Mississippi is the opposite of New York, right? I'm literally going from Mississippi to the middle of Manhattan. And when I tell you that I expected it to be an extreme culture shock, and which it was different from what I was expected to be a part of. But the moment that I got there and I was able to meet everyone else, and everyone came from different walks of life. We had people from California, we had people from Washington, they came from all over. And we were just like, well, you know, we've got some money in our pocket, we've got the city, let's do something. And within the same day, we were all connected, and we created that friendship in that environment. And it lasted. 2 years later, we're still here, like excited to meet up with each other and excited to do things and excited to hear about what each other's doing. I'm still in undergrad, but we do have students that are now in grad school, and we want to hear about their research and their accomplishments. So I really think creating that lifelong bond, it surprised me. It's not what I expected at all.
Yeah, I can go next. Two things were just really surprising to me. The first, just the work culture, just the idea of going to work. You know, for me, I don't even know how I got into physics, and I didn't know what I was going to do with it. I was like, I don't want to be a professor. I can't teach anything. I can't teach myself. What can I do? And just to go to New York, I'm from Chicago. I love big cities. So I'm like, I love New York. I want to live a city lifestyle, and to see that in the middle of the city, there's this huge institute of physicists. I'm like, that's perfect for me. Like, I can do something and not be in some lab somewhere. I don't know, or figure it out. But another thing that surprised me, which just really goes to Saran, Casey, and Shannon. They really were invested in us, invested in our stories, invested in our experiences. And I think that made it 1,000 times better. They just really always checked in on us, added things to the program, wanted to hear our feedback. And I just really enjoyed that, because I've been in programs where it's like, yeah, those are our advisors and supervisors, but they don't really care, but they truly did care. So yeah, thank you to you guys.
You know, I want to say one more thing or something that was really surprising to me with the whole internship at Simons Foundation was pretty much how fast we got integrated into the cutting edge of science and physics in whatever respective field we were in. Like Jade said, the day we got there, essentially everything was different. It's like it jump-started our careers as scientists. We were treated as guest researchers at the institution by every single person who was in there. we always had someone who we could go to. We could just walk up and knock on the doors of these cutting edge scientists and ask them a question about our projects that we were working on pretty much anytime we were in the same place.
They did not underestimate us at all.
Not once, not once. And it's like the amount of confidence that that could give you so fast and so early on in our careers, it was shocking. Changed everything after that.
Yeah, and I would definitely resonate with what you all said, saying that having been like there for the summer kind of like you said, jump started our careers, or really gave the impression like, okay, like, yes, I'm a student during the academic year, but I feel like, you know, a professional researcher now. And like, this kind of guides me towards like figuring out like, I think, yeah, this is what I want to do. And also that, you know, whenever it's back to the classroom, that I can keep that in mind that, okay, this is what I'm in it for. This is, you know, the end goal is kind of in sight, and it's been illustrated better through this program and definitely through the support network as well.
Cool. I think there was a question online.
So by your experiences with the Simons-NSBP Scholarship Program, what do you want mentors, colleagues, or graduate students to improve to make your study or research experience more pleasant or make the place more attractive to you and other students?
Did anybody want to tackle that?
I'm sorry, could I hear the question again? There's a word or two there that I didn't catch.
Sorry, I have to go back to it. I lost it. And thank you, Zena Online, for the question. So it says, by your experience with your program, what do you want mentors, colleagues, or graduate students to know to improve your study or research experiences to make it more pleasant or make the place more attractive to you and other students?
Yeah, I would say that I would want them to know, and I think that they did know for a good part, that understanding that, you know, that was for me, like, you know, one of the first times of like living on my own, or like being like, I don't know, there's an element of me that's like, I'm still pretty young, like I'm curious, like there's a lot that I want to do, but I think they saw that, and at the same time, you know, treated that with care by, you know, whether it was like, you know, not imposing too many demands or like, you know, stressing us out. But at the same time, like understanding that, you know, affirmation that it's like, it's okay. Like if this doesn't work, like, you know, you're still very, very, very early in your career. Like this is the way you're feeling, the way you're thinking is totally normal. So I think just affirming that for some of us that, you know, we're still in undergrad and whatnot, that, you know, things will get tough, and that there are people there that can help us, and that nonetheless, you know, if mistakes are made or things aren't working, that's totally part of the process. So that affirmation is really helpful, and I was glad to find that in a lot of people.
I agree with what he said. I think I can speak to this based on something that my mentor did that I can recommend for other mentors, because I know each student usually has their own mentor. So I worked with Dr. Mark Devlin at University of Pennsylvania, and I was on an instrumentation project with the Simons Observatory. I don't believe that was what he originally had in mind for me. Usually professors go in, they kind of type something up and say, oh, this is kind of what they're going to do. And then whatever student I get, I'll just give them that project. And we did preliminary meetings to kind of get to know each other and to talk before we got to New York. And I told him, I said, I'm kind of interested in instrumentation. And he said, oh, well, that's not what I had planned for you, but that's okay. And the project changed. Now, what he had planned for me became a part of the project, but he made sure to incorporate what I was actually interested in. And I think that could be very important for other mentors to understand, is you have to fit the project to the student and not the student to the project. And I think students, of course, they have different interests. They learn in different ways. They grasp things differently. Different things pique their interest. And when you see that a student has an interest, run with it. Don't just force them into a project. And I think my professor did a very good job of doing that. And he supported me 100% along the way. So, yeah.
Yeah, Morgan.
I have a question.
So I was wondering, we're hearing from you guys and you're all clearly very impressive, qualified people. And I'm sure there's many people who are interested in this program, but are perhaps nervous to apply and maybe feel like they won't be accepted or they won't be prepared, which I think is what a lot of you felt going into this program. So what advice would you give to someone who is interested in applying, but maybe hesitant?
I have wait, are you reading my notes? Because that was like legit, exactly my next question.
I'm just reading your mind, yeah.
Yeah, I can speak to this perfectly because it was literally that winter break before the summer. I was at home on my floor crying because and emailing my advisor back at Davidson saying, I don't know what to do for the summer. I haven't taken any of these classes that these programs are listening. I don't have this GPA. I don't have this experience. I don't know what I'm doing. And he emailed me back and he was like, Jay, be quiet. You're fine. Just apply. Here's a list of programs you should apply to. He's like, I have your recommendation letter. If you want me to look over things, I'll do it. Like literally just apply to anything. And I did. And this was definitely a program I was like, I'm not getting in here. I don't know anything about coding. I didn't have experience before that. So I'm like, okay, I don't even know why I'm applying to this. But I got that letter, I got that email saying you're in. And I was like, wow, that's amazing. And so to that, and he was telling me this before I left for this conference, he was like, remember what I said last winter? Just apply, just do it. It's better to do than not to do it. So just literally just do it. Yeah.
I want to emphasize the fact that this internship is the perfect place to be, to have questions about what you think you want to do with the rest of your life. You're around some world leaders who know exactly what this field that you may have an interest in looks like. And they are all there dedicated to making sure that you get the answers to the questions that are burning on your mind. I remember for me, when I was applying for this internship, my advisor just reached out to me because I was also panicking about trying to figure out what I was going to do with my last summer in undergrad. I felt like I was running out of time. I wasn't entirely sure exactly where I wanted to go. I knew I had ideas of things that I wanted to do, but never really knew what to do with them. I was worried that my GPA wasn't good enough, was worried that test scores, and was just worried about my coding ability and all that. And he said, just apply. I already wrote your letter and sent it in. So you kind of you don't really have an excuse now. They're expecting it, and just see what happens. That's really all you can do. And then after that, you just sent it in and was fortunate enough to get that letter back. And then ever since then, it's been totally different. It's like, how can I say this? I guess the fear of jumping into something that seems so academically rigorous is a little bit scary because you don't want to go out there and make yourself, for lack of a better term, look like a fool. Or you don't want to go out there and feel like you're looking like a fool. And that is not at all the environment at the Simons Foundation. You go there and it's like every question has value regardless of where you are in your career. And the only thing they're really looking for is someone who is willing to ask that question and willing to take a conversation on following that question.
Yeah, and I would also add saying like for me, I definitely struggled with like the idea of like, should I even like apply? Like I'm kind of like stuck. Like, is this like it takes a little effort, to put that together, and it's a big mental hurdle. But I've had like mentors in the past just say that that's half the battle. Like if you don't apply, you're rejecting yourself. You know your answer. If you don't apply, it's no. So if you get over that, and that's not the easiest thing to do, but also knowing that you're definitely increasing your odds if you apply at all. So that kind of gave me some hope.
And I'll add one more thing. The questions for most applications are usually around the same. So really you're just writing it once. It's like applying to college, which we all have done. So, and now you're not even paying for application fee. You're not paying for that or SAT fees or anything like that. Just write a general personal statement, write those general prompts and copy and paste. You're good. And then ask for those recommendation letters, which somehow we already have. So yeah.
Let your confusions drive you. Don't let them stop you, and just see where they go. Because at this point in our careers, it's like this is the perfect time to see exactly where our confusions could lead us. It might be something beautiful.
I think every scholar in this room can speak to this, every NSBP scholar, but that application gets you so much more than just the REU. once I finished my to my time at Flatiron Institute, it opened other doors. It got me back in New York this summer, to meet the new scholars. It's opened so many doors for me. So I think you fill out that one application. And even if you don't think that you can do it, be delusional. Do it anyways.
100%.
Like, I've done REUs where their research that summer was their first time even seeing physics. They hadn't even taken a physics class yet. They were physics majors, never taken a physics class, still did the REU. If you can get into a physics REU without even a physics class on your transcript, and you have all of the physics classes and you have recommendation letters and you have experience, then you can do it 100%. I know me and Morgan, we were 19 at the time. We were just getting our foot into the door. We were just starting even basic classes like classical mechanics and things like that. So it's 100% possible for everyone.
I think, yeah. There's some randos got a question.
Hello. Yes, yeah. Rando dude. Have you talked about Stefan yet?
We have not talked about
All
Stefan.
right. So because like there's a phenomenon, you guys are all incredible. I got to meet them in 2021. And the experience from us professionals is one day you're our summer student, we blink and you're our colleague. We blink again and you got white hair. So I'm going to start talking about the next steps, because when did this program officially start?
What year?
Yeah.
2020.
2020. Let me tell you when it really started. I don't know when it really started, but Stefan Alexander, I met this brother in the early 90s, and he told me this vision. He told me about issues that we have within the African-American community, such as there can only be one, right? And he gave me a vision of bringing people together, students together, colleagues together, and creating a cohort that saw each other as a support system and colleagues that you could work with and publish with. And then he went about his career and he made lots of relationships. So I always talk about skills, knowledge, and relationship, but there's also hope, hustle, and help, all right? And what Stefan did is he got to know Dave Spergel, who's the president. He got to know Jim Simons. And when he became president of the NSBP, he found himself in a position where he could make this dream become a reality. Where you at in school again?
Stefan's office at this point.
There we go, right? And how many of these students have Stefan published with at this point, right? So what I'm saying is that some of you today can create that same vision. You can create that vision for how you want to change this community and take it to the next level. And so 20, 30 years later, you will have your cohort sitting up here, all with Nobel Prizes, right?
Yeah.
And platinum albums and Oscars and Emmys, all that stuff, right? But that I just wanted to Stefan's not here this time. And I just wanted to call him out because this brother's been working on this for so long, and what he has helped create with this partnership. And you remember when I gave my keynote, I said isolation is death. And another thing that we have in our community is this idea that I got to do it myself. And this idea of, it got to be all Black folks. Casey ain't Black. How do you feel about Casey? Does Casey love you?
Oh,
Yes.
Yeah, every time I see Casey, he gives me a big tongue kiss. All right, that's just a joke. But
Every other time.
no, he gives me a big frustration. Hakeem, you don't answer my calls, you don't answer my emails. I'm like, welcome to the club. But the point is that it's through these collaborations, it's through these allyship. We are all individuals. We're not racist. We're not a field. We're all individuals. And there are a lot of people in this world who have great hearts, who have the same mission that you do. And the more we create these bonds and the more we create these collaborations, the more we can have brilliant people. Like when I met a sister from Jackson State University and the Simons Foundation, I've been on Jackson State University campus a lot. So I went to Tougaloo. And I tell you, I almost burst out in tears. But I'm pretty hard, so I don't actually cry. But it's a beautiful thing is what I'm saying. And it didn't happen by accident. And so, following the footsteps of Stefan Alexander, but also following their footsteps, because Dave Spergel wants you, Jim Simons wants you, Casey wants you, Saran wants you, right? So come join them. And the beauty of it is when you start something like this, older people like us, we already see it. We already see where you're ending up. We already see the success because of how you carry yourself, how you go about your work. But you probably can't see it because you're in the hustle and you're needing the help, right? But it's already happened. It's already come to fruition. And, you know, let's keep it going. That's all I have to say.
So actually with that, I think we're supposed to wrap this up at 4:30. So Rafiwe, you may have had another quick, maybe a question we can. So I'm going to pause and let them transition on Zoom. And then after this, you know, and then we'll take that question. We're going to have a break. And then after a 15-minute break, then we're going to talk about how you can become involved if you're out there, whether you're a prospective scholar or you are somebody who is, you know, already a faculty member. So Jessica, just let me know when we can ask that question.